Okay, so today is week two, right? I'm sharing the screen. Yeah, excuse me. Uh, so I am Anmol Biswas. I'm a PhD student at ITV, and a PMR scholar. I'm doing these sessions, weekly sessions like tutorials to help you solve assignment problem and such, right? So yeah, and today is week two. Today we'll cover the uh, basics of learning systems. Right, you're doing deep learning, so we'll start with like the basic components of a deep learning system. Right, uh, we'll see some problems relating to those things. We will also yeah, mainly we'll see kind of problems relating to the basic components of a deep learning system, right? And uh, like how many parameters typically will be there in such systems and things like that, right? So without further ado, let's start. So here are the components of a generalized, what I'm calling a generalized learning system, right? The basic idea is that there are basically four components that are common to all kinds of learning systems, right? It does not matter if it is a SVM or a deep neural network, anything that has this property of you learning from the data, right? So what are these things? First is very obvious. You need data, which is training and test, right? So you have X, which are the inputs, and YL, which are the label outputs. So it is not necessary to always have a labeled outputs given from externally given, right? Uh, when labeled outputs are available from an external source, right? And then you can train your model on those labeled outputs. That is called supervised training or supervised learning, right? Not all types of learning fall under the supervised learning category. For example, you could do with like, for example, you have these large learning models that have come up, right? And there is no strictly defined label that they have. So what they do is they just take all of the information and they train the model as a predictive system, right? So the label then becomes given a context, the prediction of the next word or the next token, things like that, right? So so this label while don't take it as a as a point of fact, right? Generally speaking, in supervised learning, which is mostly what you will cover in this course, you will get labels, but generally speaking, it may or may not be there, right? Of course, the inputs have to be there, right? Data has to be there for your model to learn anything, right? The second thing that is important are the parameters, which are how your model is basically described. The parameters basically describe the state of the model, right? And typically parameters are divided into weights and biases, right? Weights are the linear transformations, biases are the affine kind of shifting variables, right? Excuse me. So weights and biases, and collectively parameters are usually referred to by this symbol theta, right? So when you say that, we are taking loss with respect to theta, it just means you're taking the loss with respect to, taking the gradient of the loss with respect to, let's say, weights and biases separately, obviously, right? So the third thing that you have so this is a typical of deep learning systems. This is called an activation function. which is usually denoted by this symbol sigma, right? So activation functions are, like I said, typical of deep learning systems. The other thing, which is a loss, is common to all kinds of learning systems, right? So, this loss basically parameterizes how good or how bad your model is to map in mapping the data, right? So loss gives you a sense of your direction, or how bad you are or how good you are, and how to improve that. Activation functions typically, function is something that is present in deep neural networks. We'll come to why we need activation functions later. Weights and biases describe your model, and data is what you train, right? So with that set up, let's see some questions, right? So the first question is very fundamental, right? So the question is, how do you learn these parameters, right? There has to be a heuristic or a rule that you typically use, right, to learn these parameters given data, the loss, and given the data and the loss, basically, the data and the labels and the loss, right? So if you consider, so this is a very simple example. It's a one-dimensional thing. So you just have one value of weight, right? And given this, let's say you have a loss function that looks like this, loss curve, is also called as a loss surface. The question is, how do we determine the change in W such that uh, this loss value is guaranteed to be reduced, right? And then have a bunch of options. And the way I generally do these sessions is that uh, I introduce the problem. It's typically an MCQ type problem, and then I give some time for you to figure it out. This one should not be difficult. Uh, so yeah, go ahead and try to figure out what the solution is, and then you can reply in the messages. And then a couple of minutes later, I will discuss the solution. Okay. Uh, so this one should not have been a very difficult question. I don't know why people have not answered, but anyways, let's go ahead and solve this, right? So if you look at this situation, right, you are situated at this blue dot, right? You have this amount of loss, which is obviously not the minimum. We can see that minimum is somewhere over here, which means what you need is to go in this direction towards the left, right? Towards the negative x-axis, right? And then you look at the options, you can kind of figure out what is happening, right? So loss is positive, certain of these options will give you the correct direction, but not all of them have obviously the correct logic behind it, right? And so the correct answer, of course, if you have attended the classes, you know this. Uh, the correct answer is option D. Delta W is negative of the gradient with respect to weight, gradient of the loss with respect to weight, right? And why is this why does this happen? Basically, if you look at this, if you look at this diagram, you'll fear you'll figure out that this rule always corrects in the always points in the correct direction, right? Because by definition, it it has to point in the correct direction, right? Basically, if you look at this part, which is the red half of this uh, plane, of this area, uh, delta Ly gradient of loss with respect to weight is greater than zero, right? Because loss is increasing as you increase the weight, which means the negative of the gradient will be towards the negative negative w axis. Similarly, if you look at this side of the loss surface, right here, the loss is decreasing as you increase the weight. So here, if your blue point was somewhere over here, it would have pointed towards the right, towards the positive w-axis, right? And thereby, basically, what it will cause is that it will try to reach this point of minima where the gradient is zero, and then it does not have to move anywhere at all, right? So this is a very so this is a this, if you look at it like this, it seems kind of trivial, and seems to be a trivial relation or a trivial conclusion, but it is very profound actually. And this is the basic idea that is foundational for everything that you have, right? Everything, all kinds of deep learning models, all kinds of even standard learning models, right? This heuristic of a gradient descent is basically is the one way that people have, which allows them to explore the parameter space kind of efficiently in search of a solution, in search of a optimal configuration of the parameter values, right? So this is gradient descent, and then of course, this is a very simple uh, setup, a very simple heuristic, but to make this thing work, you have to do a lot of things, right? Because then you'll come up with a lot of different problems that can show up, and then you have to deal with all of those issues, and then you have to figure out the correct rate of travel. How do you travel? How do you change the, let's say, velocity by which you're going in certain direction when you're doing gradient descent, right? So all of these things, all of those things will come uh, eventually, right? As you go through, as you learn more and more about these systems, right? So let's move on to the next question. So this is about loss functions, right? Which was the fourth point that we discussed when we talked about components of a learning system, right? And here, basically, you have some options of functions, right? So there is one which is a kind of a linear. So basically, the loss functions is always a function of the output and the label, right? Uh, Label, of course, like I said, may be self-defined, uh, semi-supervised or unsupervised learning, or it may be provided from an external source, which is like supervised learning, right? So first function is just y minus yl. Next is y minus yl. So yl is the label and y is the output, right? And then option B is y minus yl squared. Then C is, so H, when you see this capital H, it usually refers to the Heaviside function, right? Which is the step function, stepping at zero, right? It is h of x equals 0 for x less than 0 and 1 for x greater than or equal to 0. And then you have this thing, y minus y is a modulus function, right? Which is absolute value uh, of of the of whatever is inside. right? So the question is which one is a valid loss function for a learning system, right? And the points that you are trying to figure out are what are the properties of a valid loss function that need to be satisfied, right? So once again, I will give a couple of minutes, a little bit of time for you to walk through it, and then we will discuss the solutions, right? And I will talk about the properties that a valid loss function should have. Hmm. B. Okay, so let's see a couple of answers. So B is indeed one of the valid loss functions, right? Which is, if you have if you're watching the course videos, you'll know that this is the so-called mean square error loss, right? It is square of the difference between your output and square of the difference between the output and the label, right? Indeed, this is indeed a loss, but more important question remains is that what defines the loss, right? Obviously, loss has to be a function of output and the label, which all of these are, right? The second thing is that the loss must have a minima, right? And the minima should coincide with the situation when your output matches your label, right? Which uh, B satisfies this, right? C, which is the heaviside function, does not satisfy this, right? Because you know this is like it's a step function, right? So it does not really have a minima. It just has a zero region, for all of those cases where y minus yl is less than 0, and it has a 1 for all of those cases where y minus yl is greater than equal to 0, right? Or you might say that it has 1 for y minus yl is greater than 0, and so typically this is how you do this. H of x is equal to 0.5, and also h of 0 is equal to 0. This is how you typically describe a step function, right? In such a way that it is still kind of continuous, well defined, right? So obviously C does not have a minima, it doesn't have a proper minima, and it does not align with y equals to yl, right? A also does not have this, right? Because it's just linear y less y minus yl, right? It has no minima at all, in fact, right? So, but why have I so of course D also has this minima term, right? Because when y equals to yl, you get value 0, and for all other values of y, you get a positive value, which is greater than 0, right? So it does indeed have a minima, right? But why have I kind of marked it out separately from B? That is the second thing, which is that loss function must be differentiable, right? Y minus y square, or y minus yl whole square, of course, very well known differentiable function, right? It's just a square of the difference. So you can easily take the gradient of this, right? Gradient is nothing but y minus yl, 2 times y minus yl, right? So you can very easily take the gradient for this, but when you take a modulus function, right? The gradient of the modulus function is not defined, technically not defined for the point where y equals to y, right? For that point where the output matches the label, the gradient of the function is technically not defined, right? Because it's a 1D norm, right? And if you actually plot the gradient everywhere else, you'll get something like this, right? If you plot gradient of loss with respect to y, and on the x-axis if you keep y minus yl, this is for option D, right? So if you plot it like this, you get a positive 1 for y greater than yl, right? You get plus 1, and for y less than yl, you get minus 1, right? Because that's how this function works exactly, right? The modulus function. And the problem is that at 0, this gradient is not defined, right? But so here is where a little bit of practicality comes into the picture. So this is actually a very commonly used a loss term, right? It is used, in fact, for image generation, or at least it used to be used for image generation uh, applications, right? Where you take multiple degree norms of the pixel differences between the generated image and the target image, right? So something like that. And the way that we get around this non-differentiability problem is that we define the gradient to be 0 at y minus y equals to 0, right? So basically, if the output matches the target, we just define that point to have 0 gradient, and that way our problem is kind of solved, right? Because if if we do arrive at that situation, we don't want to move it anywhere. So setting the gradient to be zero does like it solves, it does what we want it to do essentially, right? So yeah, like I said, option A obviously does not have a minima. uh Option C is non-differentiable. It also actually does not have a minima, right? uh B and D can technically be used as a loss function, with a caveat that for this modulus function, you have to separately define the gradient at that non-differentiability point, right? And once you do that, you're kind of set. So yeah, so this is about loss functions, very brief introduction, but it's also very important because you are seeing these things, right? You are seeing these uh, properties that these functions must have in order for them to work as loss functions, right? So next time you think of a loss function, you have to keep in mind, okay, I need something that has that has a minima, that is differentiable, and the minima aligns with the situation when the output matches the level, right? So these are the three primary kind of properties that any loss function must satisfy, right? And if there are like point non-differentiabilities, that is fine, right? Because you can define the gradient based on what you expect the model to do at those points, right? So moving on, we'll go to another part of excuse me, we'll go to a different part of the generalized learning framework, right? Which is the activation functions. And we'll start off actually from where we left off in week one, right? Week one, we covered perceptrons and all those kind of old models. And obviously, for the perceptron, you can say that the activation function was the Heaviside function, right? Which is the function that we just saw earlier, which is if the input is greater than zero, you get a one. If the input is less than zero, you get a zero, right? And the way that this you can make this the connection is by taking the for the perceptron, you have the weighted sum of the inputs and you subtract the threshold from it, right? And if you take that value and put it into a Heaviside function, the output will give you the perceptron input basically, right? So yeah, but the problem which we saw in the previous slide also, of course, the Heaviside function is not differentiable, and such, we cannot really have this perceptron activation function in our deep learning systems that that we want to build, right? Because essentially the idea is that we're going to have a big model with multiple layers feeding into each other, right? And because you want to train them with gradient descent, you should be able to uh, generate the gradients for each of those layers for each of those parameters that you are using in the model, right? So differentiability is a very big kind of very big deal, very important consideration. Uh, but of course, if we start with Heaviside function, we can then make it smooth, right? So that it will become differentiable, and that is exactly what is done. So once you try to make the Heaviside function smooth, you come up with this function called as a sigmoid function, right? And it's very simple. It just goes 1 upon 1 plus e to the power negative of something, right? And this whatever is inside this e to the power negative, that is basically your inputs plus parameters, the combination of them, right? So here is one question: if b is equal to 0, if you set this bias term to be 0, what is y at x equals to 0? So you can set x equals to 0. Imagine that this is just a single input, single weight system, right? You can set x equals to 0 and try to figure out what y will be. It's a very simple problem, right? Obviously, this is zero 0.5, right? Because if you set x equal to 0, you get e to the power uh, e to the power 0, which is 1, and then 1 plus 1 is 2, 1 by 2 is half, zero 0.5, right? And this is actually kind of important because is y equals to zero 0.5 uh, refers to what is called as the transition point, right? Essentially, if you are going to use the sigmoid function as some kind of a predictor in the final output layer, the way you do it is that you can consider your two classes, right? Your positive class and the negative class. And if your output value is higher than zero 0.5, you say that it belongs to the positive class. If it is lower than zero 0.5, you say that it belongs to the negative class, right? And this is exactly analogous to using a Heaviside function, right? We would get the exact same output if you had used a perceptron instead of using the sigmoid activation function. If you had, so basically, if you set uh, this threshold as, the point of transition as this zero 0.5, the output is basically exactly the same as what you would have gotten using a perceptron, right? So that's why this value transition point thing is important. So moving on. Mm, yeah, so the next part is a little bit about uh, the nature uh, of this uh, activation function, right? So consider you have this model, right? You have x is your inputs, w, w transpose, basically w is your weights, right? And then you have output y, which is applying the sigmoid activation function over w transpose x, right? The question is which parameter enables the model to learn from the given data, right? Is it x, is it w, is it both, is it none? Right. So this is very simple. The problem should be able to answer it very quickly. I'll just give a couple of minutes max. Okay, so yeah, like I said, this is a very simple problem. Obviously, the parameter that allows you to learn from the data is W. Is W is the weights, right? X, of course, is the data itself, right? So X is not the parameter, right? Which is very important to keep in mind. Yeah. X is the data, W is the parameter that describes the model. So that's where, uh, right. So moving on. So here we are going to look into some characteristics of the activation function, right? So for example, which of the following functions cannot be used in a machine learning model, right? And here we have, we have certain functions, right? We have y equals to w transpose x, x transpose w transpose x. You have this, which is just same as the sigmoid activation. You have this y equals to 1 upon 1 plus e to the power minus x, right? And the question is, which of these functions is not a valid, function that you can use in a model? So for this question, we will discuss, some of the properties that an activation function or any kind of function that you have inside uh, that you have describing a layer must have, right? So yeah. Mm, uh, okay, no one has answered, but we'll carry on, right? So what are the important parts of function that you can have in a machine learning model, right? Obviously, it has to do something, right? And it has to be able, it has to have some parameters that you can potentially learn from, right? Or that you can potentially uh, learn, right? And the third thing, of course, is that it has to be a differentiable function, right? Because everything depends on differentiability. So let's look at them one by one. First one is linear transformation, right? You take y, you just multiply, you take x, you just multiply the weight matrix with x. It will transform the vector from, depending on what the values of the weights are, to generate a new vector, right? And this obviously is kind of obviously like the building block of everything that you have, right? Linear transformations, and then on top of that, typically you have non-linear activation functions. But in some cases, even you might want to keep these linear transformations undisturbed, right? And we'll see in later times, when there is a situation that you actually don't want an activation function on top of this output, right? So this is obviously is fine. This is a layer that you can have in your model, right? It is differentiable. It has parameters to learn, right? The second one is a slightly different, uh, you know, setup, right? It looks different than what you would have normally seen uh, as examples, right? But this is also fine, right? Because even though it looks different, you have to keep in mind what are the properties that we are looking for. The first property is that you must have some parameters to learn, and of course, this has these parameters, right? It has this W matrix. Second is that it has to be uh, differentiable, which of course this will be differentiable, right? Because this is nothing but just the quadratic transformation, right? It's just taking it's basically like taking autocorrelation with some weights involved, right? It's a weighted autocorrelation. So this is also uh, differentiable, has parameters, so this is also fine. The third is of course your sigmoid on top of linear. So you have a linear transformation over here, and then you apply the sigmoid function, which is an activation function, on top of it, right? So this also ticks all the boxes. The fourth is where you know it's not a layer that you would ever have, right? Because why is it not a layer? Because there are no parameters here, right? There is nothing to learn. There is no parameter to optimize in this layer, right? So this transformation is typically something you'll never have separately as a layer, right? Because there are no parameters. And like I said, these are what the other transformations are. First one is a linear transformation. Second one is by the same an extension. It's a quadratic transformation. The third is a sigmoid activation function applied on top of a linear transformation, and this is nothing, right? So yeah, so activation functions need to be uh, not activation functions, broadly speaking, layers need to be differentiable. So specifically, the activation function needs to be differentiable, and they need to be parameterized. That is, they must have some parameter that you can learn, right? So here we kind of deal with some of the properties. Who's this? Yeah, yeah. Uh, no, right? It's not like a point non-differentiability, right? It's like uh, it's generally it does not have that pattern where it kind of forces things towards your minimum, right? Towards where you want your model to end up, right? Which the L1 norm does have, right? If you think about it, it's like it's like a if you think about the loss surface as an actual topology, then the minima, the L1 norm, which is the modulus of y minus yl, is kind of a sharper version of the L2 norm, which is y minus yl squared, right? So yeah, so yeah, it has to have that generalized kind of appearance as well in some way. Yes, yes. Okay, thank you for the question. Because that was a uh, good question. Uh, okay, so here we are looking at characteristics of a uh, sigmoid function, right? So let's say you have this setup, right? You have this sigmoid function setup, W transpose X plus P. Uh, you can imagine that it's just uh, one parameter, right? So W is just one value, X is just one value, right? So what happens uh, if the value of B is increased, given that W is greater than 0, right? So here you just think about how that function that we saw in few slides earlier, how that function is supposed to change when you increase B in this under these constraints, right? That W is greater than 0, right? Excuse me. What did we say? Excuse me. See. Yeah, so obviously, so let's kind of clarify something. Obviously, the what is going to change if we change the B is the transition point, right? Because imagine that B is set to 0. If B is set to 0, then what is the transition point? Transition point is nothing but x is equal to 0, right? Similarly, and then imagine, b is set to something else. uh, let's say b is set to 5, right? So you go from 0 to 5, which is an increase. And what happens to the transition point? So understand that for the transition point, basically what you're looking at is this equation that wx plus b equals to 0, right? So you said b is equal to 5, then basically your transition point becomes x is equal to minus b by w, minus 5 by w. Here I have stipulated that w is greater than 0, which case your transition point is now negative, right? So it is no longer 0, it is some minus 5 by w. And what this means is that your transition point has shifted towards the left, right? Which is exactly what you would get if you actually, if you, for example, plotted the sigmoid activation functions for two different b values, right, with a positive weight. So if we do this, you'll find that it does indeed shift towards the left. What this means is that the input for which you're switching the class, right? So the input for which you are kind of changing your decision has become, you know, has become more negative, right? So you're changing a decision earlier if you're thinking of going from negative to positive, going from lower to higher values, right? And thinking of where you change your decision from, let's say, negative class to the positive class, then basically what is happening is that this bias is making you change your decision earlier, right? And similarly, it would be, if the bias is a negative number, then you're changing your decision at a later point of time, right? Because essentially what is happening is that when in this red graph, when your value, when your input is over here, is when you're changing your decision, whereas in the original, it was when your input was over here that you were changing your decision, right? So things are shifted over here. So the next question uh, is an obvious corollary to the previous one. Here also we have the same setup. We have the same condition that w is greater than 0. So the question is what happens when the value of w is increased, right? So here we are keeping the bias as constant and we are changing the value of the weight, right? So the question is what happens if we do that. Yeah. So based on the previous discussion, we can obviously immediately cancel out some of these options and think about the rest, right? uh, yeah, so here basically what's going to happen, of course, like I said, okay, hinted, uh, you can immediately discard uh, B and C, right? Because when you're changing the weight, when you're if you keep the bias constant and you change the weight, it does not change the transition point, right? Uh, yeah. So what happens instead is that the slope of this decision, right? It either becomes steeper or it becomes less steep. And in fact, what happens when you increase the weight, that is a positive value, is that the slope becomes steeper, right? Which is kind of a common sense conclusion that you would go to, and yeah, that's what happens, right? So we'll move on then from these kind of toy examples, and we'll see something. We'll consider a problem that you might actually have to think about, right? And we will see like a real life example of this, something like this also, uh, once we are done with this, right? So consider a simple neural network, right? This is a so-called two-layer neural network. You have uh, input layer, you have hidden layer, and you have output layer, obviously, right? So you have input layer with 5 input neurons, you have a hidden layer with 9 hidden layer neurons, and you have output layer with just a single output neuron. The question is how many total parameters are there uh, for you to train, right? And you have some options. Uh, I want everyone to try and work this out. This is a very typical kind of problem that you might come across, right? And it's always good to be able to figure out the number of parameters that you that you have in a model, right? So you should be able to figure this out. Uh, yeah. So once again, I will give some time and for everyone to work it out by themselves, and you can post the answers in the chat, right? And then later we will discuss the solution. Excuse me. Mm. Okay, let's see. 64, 4. Okay, so 60. I'll just say in advance what is the correct uh, answer here. 64 is the correct answer, but we will build to it in a step-by-step manner, right? So first of all, let's kind of draw this. Let's draw this neural network, right? And we'll put in things as and when we kind of figure out what they are. So first of all, there is a input layer with 5 neurons, and there is a hidden layer with 9 neurons, and finally there is a output layer with 1 neuron, right? And here you have to figure out how many parameters are there in this layer in between input and the hidden, and in this layer in between hidden and output, right? So first of all, in between the input and hidden, how many weights are there? There are obviously 5 times 9, which is 45 weights, right? But that is not all, because there are 9 biases as well. Each of these hidden layer neurons will have a bias, right? So basically what you end up with is 5 plus 1 times 9, which is what, 6 times 9 is 54, right? So you have 54 parameters over here, and then go to the next layer, which is just hidden to output. And of course, because there is only one output, the number of weight parameters is 9, and the number of bias parameters is just 1. So totally there are 10 parameters over here, right? So there are 10 parameters here, there are 54 parameters here, uh, which together come to 64 parameters, right? Which is, like I pointed out, the correct answer. So yeah, so this is typically how you count the number of parameters. Generally speaking, don't you should always remember that neurons have a bias term, right? So every neuron will have one bias term, right? So whatever is the size of the layer, that is also the size of the that is also the number of bias terms that you're going to have, right? So we will stop here. I will take some questions if you have. And then a bit later, we might look into a kind of hands-on example at the basic level of deep neural networks. Excuse me. So yeah, so that is the questions material for this week. If you have, like I said, if you have questions, you can ask them. You can take, rather I can take. So in the previous session, I had shown this website to everyone and shared with everyone here as well. It's nice. It's a fun website. You can see playground, neural network playground website, right? So you can do all kinds of things there. Try out, see, verify your intuitions or the concepts that have been taught in the class in certain extent. Right. So for late joiners, I will quickly go through what was covered once again in this session. So the first thing that we saw is this the basic components of a learning system, right? Obviously, you need data, which is inputs and the labeled output. You need parameters, which are the weights and biases, collectively referred to as theta. You need an activation function, or rather, you need several activation functions, right? Because you're going to have multiple uh, layers in your network, which are usually parameterized by the sigma, and you need to have a loss function, right? The loss function basically tells you about the quality of your model, right? So the second part is given a loss, uh, how do you generic like how is it what is the generic method to kind of reduce the loss, right? How do you make an incremental change or an incremental update into your model such that the value of the loss can reduce? And we saw that the way you do this, which is the heuristic upon which all of learning is kind of based upon, is this thing called gradient descent, where basically what you're doing is you're moving in the reverse direction of the gradient, right? And to show that, we have this very simple example here, with a single parameter loss, right? Loss kind of looks like a square term, and what you have is, you know, you have a situation where you're basically trying to roll down the slopes of this loss so that you end up at the valley at the bottom, right? And if this is the minima point that you're looking for, then of course you have reached it. And the way you do it is you go in the negative direction of the gradient, which is, like I said, reverse of the slope, right? Next, we saw some characteristics of loss functions, right? The properties that loss functions need to have uh, in order for them to be valid loss functions. And we saw that basic properties are that the loss functions should have this appearance, or should have this characteristic that they have a minima, right? That the minima aligns with the situation where your output matches the labels, right? And it should be in such a way that by doing gradient descent, you should be able to kind of hopefully reach the minimum, right? And of course, the square term, so it's squared, is an obvious example of a loss function, right? Because this is also something, it looks like that. Uh, the other thing, of course, is that the loss function must be differentiable, right? And you see this one, and uh, modulus function also ends up being something that you can actually use as a loss, because it is just a point of non-differentiability, and you can define, and in fact the point of non-differentiability occurs when your output and labels match, so you can just define the gradient to be zero at that point, right? And everything else works, right? So when you are away from this minimum point, you will always push towards it, and same for this as well, right? Then we moved on to activation functions, where we started with perceptrons, the activation function of the perceptrons, which we can call Heaviside function. And we noted that it is, because this is not differentiable, we can basically smoothen it out. And the way, and by basically smoothing out the Heaviside function, we have it's called sigmoid function. And yeah, so it has a transition point at some point, and x equals to 0 if you set the bias to be 0, right? And the way you interpret this transition point is that if this where perceptron, this transition point is the point where elliptical decision, right? Gone from negative class to positive class, right? And we look into some properties of the activation functions. Uh, First property is that it must be parameterized, right? We figure out, like, obviously, if you have a model like this, what is the parameter, what is the thing that allows your model to learn is the weights, which are the parameters. X is the data, right? And then, you know, as a extension of this, we realize that we cannot have functions where, you know, where this parameter aspect is missing, right? So you cannot have this, for example, option D, because there is no parameter here that you can learn, right? Everything else, this is a linear transformation, this is a quadratic, this is maybe sigmoid, right? Then we end up in activation functions, where we just look into some properties of the sigmoid. For example, if keeping the weight constant, if you tinker around with the bias, what happens is that this transition point, right? This transition point where things kind of flip from one side to the other. So that transition point shifts in whatever direction, depending upon how we change the bias value, depending upon what is the value of the weights, right? And similarly, if you change uh, the value of the weight, what happens to this function, right? You see that slope becomes steeper, right? And after all of this, we finally come to a question which kind of has a practical significance, right? Because counting the number of parameters is always uh, something that you might be required to do. And we start off with a very simple model, which is a single hidden layer with 5 input neurons, 9 hidden layered neurons, and 1 output neuron. And we compute the number of parameters. So first of all, input to hidden, the number of weights, of course, are 5 times 9, right? Because there has to be a matrix that connects these two. So it is 45 weights, but of course, this hidden layer neuron, each neuron has a bias. So those are 9 biases. So 45 plus 9, that is 54 parameters here. Similarly, 9 weights going into the output plus 1 bias going into the output, that is 10. So you have a total of 64 parameters, right? So that's that. Uh, here starts. Yeah, let's understand. We have to something. Yeah. So let me show you something. A share the screen. Okay. So we will see a very basic example of uh, deep neural network. This is similar to the last question that we saw. Excuse me. Mm, yeah. So this is Google Colab. This is a online kind of resource where you can run uh, it's a free online resource where you can run these kind of experiments, right? So uh, they have so basically you can run Python code, and typically what you would want to run is uh, learning code experiments, training testing experiments, right? Because you can get limited access to GPUs through things like this. And of course, this is not the only thing, that's not the only service that you can use. Uh, the You can use, for example, there's something called, uh, yeah, so there's a, mm, oh, sorry, the mic was turned off. So, yeah, like I said, so this is Google Colab, it is called collab.google.com. You can search, look it up. So this is basically an online resource to run Python code, right? So they allow you to run these Python kernels. You can see over here a few resources, right? So basically, what I'm running here is Python 3 uh, kernel with Google server backend, right? So basically, this is running on the cloud, and you get a very decent uh, setup, right? You get like 12 GB of RAM, you get a 15 GB kind of, you can get like a 15 GB GPU for free, but of course it is limited how much you can use this. Mm, okay. Yeah. So like I said, so here we have a typical setup. Uh, so in Python code, you start off with something like this, where you import basically all of these libraries, right? And what we are calling here are some very basic libraries that you're going to need. First is it's called as NumPy, which is numerical Python. It helps you to handle all kinds of uh, numerical requirements, right? Matrix multiplication, linear algebra, all kinds of things, like taking scientific functions of numbers, right? So that's NumPy. The next thing that we're calling here importing is TensorFlow, which is deep learning library. It is is the one developed by Google, or rather, it is one of the ones developed by Google, right? Uh, then from TensorFlow, we have imported uh, what's something called Keras, which basically is a wrapper on top of TensorFlow. But Keras is a wrapper on top of many things, right? It's a uh, easy way to build your models, right? And basically, depending on what a backend Keras is using, it will define things separately. But the important thing is that for the user, you just interact with Keras, and then Keras handles how it has to manage things in the backend, right? So it's a simpler way to define neural networks. And then we have something called TensorFlow datasets, which is a collection of datasets that are provided by this TensorFlow. Excuse me. Yeah, and then once you have imported all of this, we'll go ahead and import one of the datasets, right? Here we are importing the dataset called as MNIST, which is a handwritten digits dataset, right? And you can see for example, some of these examples. So they look like this, right? So there's 4107, right? And we're basically splitting the data into train and test. Shuffle files. So this shuffle files basically it shuffles the order of the data that appears, and as supervised was true within full control. These are the uh, background information that you can get about the data, right? So yeah, so you're loading the data from TFTS, and of course this is the first part of the puzzle, right? Remember when we talked about the basic components of a learning system, data was the first thing. So obviously data is the first thing you're gonna get, and then of course you have to transform this data a little bit, because MNIST is images, so they are stored as uint 8, right? 8-bit unsigned integers. And what you do is you are going to normalize these values, right? So you convert from uint 8 to float 32, which 32-bit floats, and you divide the value by 255.0. What this does is that it takes this uint 8 values, which goes from 0 to 255, and then converts them into floating point values, which go from 0 to 1.0, right? And then, yeah, and then you apply this normalize function on top of your data by calling this map, and you batch it out, right? And then, so this part here is the important here is where we are kind of defining the model, right? And we'll see all of the things that we saw in that we kind of discussed, right? So first here is first layer here says what we are calling flatten, is a flatten, which basically takes these two-dimensional images, right? So our images are actually like this, and what flatten does is it converts those images into vectors, right? It converts two-dimensional images into one-dimensional vectors. It just makes one long thing. And it basically pastes every value in the two-dimensional vector one after the other until it reaches the end of the row, and then it goes to the next row and then pastes everything again, and then so on and so forth until all of the data has been written out uh, in essentially one long vector, right? So this is, of course, this is what we think is happening, but in reality, the way that computers store information, this flatten call is kind of it's just something we're telling. It's a cosmetic change, because internally the storage mechanism is such that everything is stored in a long array, right? It's just that you keep track of, what was the row size and how many rows are there. Where if you call flatten, you no longer need to keep track of those things. You just take the raw data and you can operate on it, right? And this data of the NNIST is 28 by 28, which means that after flattening, so the size of this layer, size after flattening is 784, right? So this is the size of your input layer essentially. And then in the middle you have a hidden layer where how many neurons are there? So there are 800 neurons, right? So size of the hidden layer is 800, right? So size of the input layer is 784, size of the hidden layer is 800, and of course because it's a digit recognition problem, the size of the output layer is 10, right? So size of Here is 10. So here I will pose another question to everyone, which is, of course, so this is a realistic example of the problem that we looked into uh, at the end, right? The final problem that we considered. So here, why don't you take these numbers and take this architecture and try to figure out how many parameters are there excuse in this model. Okay, so I am seeing one answer and I think it is correct. So let's see, right? Let's run this code and see what we get. Right. So yeah, in fact, 636,010 is the correct number of parameters, right? Which you get, very nice confirmation of whatever we were, whatever arithmetic we were doing, right? So let's go through the once again. Let's go through the final kind of statement here. So here, what we're essentially doing is we are uh, describing a sequential model. A sequential model is one where you have one layer one after the other. You have layers one after the other, and you describe them as such, right? You describe them sequentially, and essentially what you get after describing this model is that internally Keras or TensorFlow will basically connect those models, connect those layers together, and if there was a if there was an issue with the parameters, it will tell you that there was an issue. But generally speaking, if you are describing sequential models with like uh, the typical kind of setup of layers, generally you won't be an issue, right? You will be able to go through. Right? So here we are only using what is called as dense layers, right? Which are the other name for dense layers is fully connected layers. There are other types of layers that you can also use, uh, that we will see a lot is convolutional layers, which are typically used for images. Uh, there are other kinds of layers. There are recurrent layers also, right? Which have self connection. And finally, there is this term called model red summary, which basically gives you summary of the model that you have developed, right? So this is what is actually telling me how many parameters are there, uh, how many total parameters, how many trainable parameters, how many in each layer, right? So there are, sorry, these many here and this many here. Total number is 636,010, right? And then finally we come to the optimization. So here, this is the optimizer, right? So remember when we, so this is like, this part is what deals with the loss, right? Loss and the gradient, right? Remember that we figured out that we have to go in the negative direction of the gradient. This optimizer, which is called SGD, which is short for stochastic gradient descent, is something that does exactly that, right? So you set up this optimizer with this hyperparameter. So these things are called hyperparameters because they define, so something like this learning rate is called a hyperparameter. It is defines the performance or the learning of your model, but eh, yeah, but it is not something that you learn through the model, right? So you set up this optimizer and then you compile. So now you have created your model, right? And you have given it everything that you need for it to do what you want it to do. And you have given, so here are a couple of things that, here is mainly one thing that we have not yet seen, which is, so this is the loss term, right? And we have something called sparse categorical cross entropies. This is something we'll see in future sessions, or it might even already have been covered in the course, but we will see later in the tutorial session, something like this, what this loss is, how it works, things of that nature. And then all that is left to do is call this model.fit, which basically runs an iterative approach over uh, whatever data that you have that you want to train the model on, right? And then, yeah, is this? Yes. Uh, that is a good question. So you don't typically set the initial weights, right? At this point of time, right? I mean, that is to say, in, at this age or whatever, after so many years of development of deep learning, there are certain default initialization schemes, right? That initialize the weights, right? And you can learn about it. You can learn about, for example, something called Xavier initialization, right? Which gives you, which is typically what is used in pretty much everything by default, which will tell you, which has some like statistical understanding as to why they initialize the weights in that particular way, right? So you can read those papers. So, for example, or you can read like blog posts on the internet, or you can ask ChatGPT about it or whatever, right? So let me just say, yes, let me just mention. So there's something called severe initialization, which you can look up, which is a standard kind of initialization technique, right? Because of course you have to understand that uh, cannot, so all types of initializations will not work. So for example, if you initialize all the weights with zeros, for example, that will never work, right? Because your initialization will be very bad. There will be no output going uh, through your model at all, right? So you cannot initialize by zero. So initially people did this whatever random initializations, and then uh, random initializations worked, but you had to carefully tune the, so for example, if you're using a normal distribution to generate the random numbers, you have to tune the sigma value. If you're using like a uniform distribution, you have to tune the extent of the, you know, from where to where you're picking the values, right? And then these people who invented Xavier initialization, a few authors, researchers, so they figured out essentially a standardized, repeatable method, right, to set those uh, sigma values or extent of uniform distribution, things like that. And based on that, everything else flows from it, right? And they give like statistical insight into why they did, why things are set up in that particular way, which you can. So yeah, so here uh, our training run has concluded. We ran it for 10 epochs. Uh, yeah, sparse categorical accuracy. So it gives you a bunch of things. First thing it tells you is the loss, right? So loss is computed uh, over the training set, and you can see the loss is decreasing over time as you run the gradient descent. Next is the accuracy, which is how many samples it got right, and as loss is decreasing, accuracy is increasing. The other thing that you have here is validation loss. So basically, you are splitting the data set into train and validation, and you are running your gradient descent on the train part of the data, and you're not running your gradient descent on the validation. The validation is only there to kind of validate uh, whatever your model has done, right? And same thing is happening here. But note this kind of interesting thing here. So while train loss is monotonously going down, validation loss is actually uh, reached a minimum point here, and then it has increased, right? And in fact, it is also reflected in the the accuracies as well, right? The accuracy here, validation accuracy was slightly higher than the accuracy here. In fact, the accuracy here is even lower than it was over here, right? Which is uh, after 8 epochs, the accuracy after 8 epochs was actually higher than the accuracy ends up being after 10 epochs, and at 9 epochs it was in fact the best, which is corresponding with the lowest validation loss that you are seeing in this training run. And the reason for why this happens is also something that will be covered if it has not already been covered, right? So there are kind of interesting trade-offs that come into the picture that we have to be careful about, and then we will see how we manage those trade-offs as well, right? So yeah, I think is a good place to stop. Hmm. Excuse me. Uh, so since there seems to be no further questions, I'm going to end the call. Yeah, thank you.